A question like this is always going to be a challenge. It's very, very useful for you to take the time to read through it very, very carefully, identify what the different values are that you've been given, try to work out what you can do with them in advance, and that's going to help you to put together your route through an 8 marker. That's a lot for a calculation. Now, step 1 here is to work out the moles of MnO4-. We know what the volume is, we know what the concentration is, we are remembering to divide our 26.5 by 1000 because we need to convert our cm cubed into dm cubed. Once we've done that, we're going to use the mole ratio from the equation of the reaction between MnO4- and C2O42-. And from there, we can work out how many moles of C2O42- were in that 25 cm cubed sample. And we get our second mark there. If we take a look through even further, we've got other information about sodium hydroxide. So we can work out how many moles of NaOH there were. 10.45 cm cubed, 0.1 molar concentration. Again, absolutely vital that we're remembering to convert our cm cubed into dm cubed by dividing by 1000. But then we're going to once again use the equation, this time the bottom equation, to work out how many moles of C2O4- from the acid there were in the 25 cm cubed sample, and we get to our mark number 4. We've got 5.225 by 10 to the minus 4 moles. We're halfway. 2 of those 4 questions are marks are straightforward. N equals CV. However overwhelming the question might look as a whole, there will always be low-hanging fruit and there will always be easy wins. That's the advantage of going through the paper and working out what you can work out. Now, from there, I need to know how many moles of C2O42- were in the sodium ethane diaweight. So I've just done 2 calculations for C2O42-. You're going to take away the 5.225 by 10 to the minus 4 from the 1.35 by 10 to the minus 3, and that's going to give you a mole value of 8.025 by 10 to the minus 4. And we've now made it to mark number 5. Now, the next mark is a nice easy one because we're working in 25 cm cubed sample, but we originally made 250 cm cubed. So we get the mark for multiplying by 10, and that's a really common question that will come up. There will often be that scalability of 25 cm cubed to 250 cm cubed as part of a titration calculation. Once I've got that number of moles, I can work out the MR of Na2C2O4, and from there I can work out the mass, which is 1.075 grams. Once I've got that mass, I can compare that to the fact I had 1.9 grams of the solid mixture. So my percentage by mass of sodium ethane diaweight in that white solid is 1.075 divided by that 1.9 and multiplied by 100, giving us the 56.6%. It's worth pointing out on a question like this as well that error carried forward does play a part. So if, for example, you didn't get the balancing of the equation and you didn't get the right number of moles from that, but you went on and you did another step correctly, you would get credited for it. If you did recognise at some point that you need to multiply the moles of C2O42- by 10, even if that's wrong, because it's coming from a wrong figure, you can still be credited with that mark. And if you can show that you can do a percentage by mass of sodium ethane diaweight, even with a wrong answer, you can be credited with that one as well. So it's always worth persevering. There are many, many marks that can be picked up here. So do always try. So we're sticking with ethane diawate, and we're looking at somewhere where we're very familiar with it, which is in ligands and complexes. To answer this question, there's a huge amount of fundamental knowledge that you will need. For example, you will need to know that when we have aqueous ions in a ligand solution, we are talking about having water ligands surrounding it. And when we think about water, we have to know that there will be 6 of them in an octahedral structure, coordination number 6, and also that those ligands have 0 charge. So the charge on the complex is equal to the charge on the central metal ion. In this case, with the Fe, that's +3. Now you also need to remember that when the 2 bidentate ligands that we discuss, both of those, when we use them as ligands and form complexes, they will also form a complex with a coordination number of 6. Because they're bidentate, it means there are 3 of them, and that means that we will end up with something that looks like this. You'll notice the charge on the complex has changed. And the charge on the complex is different because it's the sum of the charges of the Fe +3 and the 3 C2O4 2 minuses. Don't forget that when you complete this, you've also got to show the water ligands that have been lost. So you've got to have that 6H2O in there. And then why is the enthalpy change for this reaction close to 0, almost 0? Well, you're breaking 6 FeO bonds. And when you put your new ligand in, you're making 6 new FeO bonds. So although they are going to be slightly different from their mean bond enthalpy, overall there's going to be very little difference between them. So the enthalpy change will be almost 0. On to 11.3, and we've got a question here about the ion complex. Now, we're doing this with the C2O4 2 minus. When you're drawing it, I would always start it in this way. Draw out your metal and draw the octahedral nature of the 6 bonds. And once you've done that, you've got the structure to build the rest of your answer from. Now from there you can see that I've drawn on my C2O4 2 minus. The minuses aren't there anymore because I've got the bonds in place. But I can see how that can be extended around the remainder of the complex. So I do exactly the same across these 2 areas, and I end up with practice, something that becomes hopefully quite straightforward and is hopefully already quite familiar with you. I'm still not finished with the complex, and that's because I've not reflected the fact that there is a charge. So I've got my charge now of -3. Now from there we're going way back to year 12 here, and we're talking about bond angles, but it is covered when you do transition metals as well, so hopefully quite familiar. The bond angle will be 90. It's an octahedral structure, and that's where that comes from. And the type of isomerism is optical. We know it's not structural isomerism because we've got a very clear and defined structure here. We know that it's not going to be geometrical isomerism because we don't have that double bond. So we have optical isomerism. Finally, 11.4, big question about ethane diawate here, and a very small question to end it. So ethane diawate ions are poisonous because they react with iron ions in the body, and they're present in broccoli and spinach. Suggest one reason why people who eat them do not suffer from poisoning. Now you might get really bogged down on a question like this. You might think, what have I forgotten? What do I not remember? Why was this not covered in our booklet, in our textbook? And it's because ultimately this is a very straightforward common sense question. If they're not suffering from it, then there can't be that much of it. If there are small amounts, if there are low quantities, then you're not going to feel the effects of food poisoning.